Good afternoon, everyone. Today we're going to find the equation of a tangent line to the curve f of x defined in this way at a specific point, namely at the x-coordinate of pi. Okay, so if we want to find the equation of the tangent line, I'll remind you that any tangent line, after all, has the equation of the form mx plus b in slope-intercept form, right? That's a line. And so we can start by finding the slope, m, of the tangent line by evaluate the derivative function f prime of x at x is equal to pi, right? And so evaluate f prime of pi. And so that means that we need to start off by actually computing f prime of x, the derivative function of f of x, and then we'll plug in our specific x value into it, right? And so if we want to differentiate f of x, f prime of x, we're going to need the product rule, right? You can think of this as your classic u of x, and cos squared is your classic v of x. And so we're going to do the derivative of the first part. That means 2x times cos squared x plus x squared times the derivative of cos squared x. I'll remind you, cos squared x is cos of x squared, right? I'll do that on the side here. ddx of cos of x squared. I'm writing in this way so you can see, you can visualize the chain rule being applied, is going to be the 2 multiplies out front, as the exponents do. So we have 2 times cos of x. The exponent will drop down by 1, meaning an exponent of 1. The exponent of 1 is redundant, and so I'm just going to leave it out. And then times the derivative of what's inside the brackets. And the derivative of what's inside means the derivative of cos x, which, as you know, is negative sine x. And so putting this together becomes negative 2 sine x cos x. I interchange the order of the sine x cos x for no real reason. It's just kind of something we tend to do in math. And so there we have it. So let's plug that in here. So we'll have the derivative of cos squared x being negative 2 sine x cos x. And now we can kind of clean that up a tiny bit. We have 2x cos squared x minus 2x squared sine x cos x. Again, that is our derivative function, f prime of x. And so that, whoopsies, that gives us the slope of the tangent line to the curve f of x at any specific value of x along the way, like at pi. And so that means that, I'll write that out, provides slope of tangent line, right? Now, the slope of the tangent line is crucial to solving this problem, right? We want to get the equation of that tangent line, and so that means getting the slope. So let's go ahead and find the slope of the tangent line at our x is equal to pi value. That means evaluate f prime of x when x is equal to pi. So let's go ahead and evaluate f prime of pi, meaning we're going to plug in the value of pi into f prime of x everywhere we see an x. And so we'll have 2 pi times cos of pi squared, right? That's what cos squared of x means. It just means cos of x squared minus 2 times pi squared times sine of pi times cos of pi. And that means that f prime of pi is equal to cos of pi, that's on the left side of the unit circle, that's going to be negative 1. So we'll have 2 pi times negative 1 squared minus 2 pi squared sine of pi, however, 0. And so since we have this term having a multiplied by 0 in the middle of it, this term goes to 0, right? And so that means that f prime of pi is negative 1 squared is 1, and so it's just 2 pi, a nice satisfying value. And so again, that is the slope of the tangent line. That's our m value for the tangent line to f of x exactly at this point in space, right? Now, to find the y-intercept, right, to find the b value, we have the slope, but we have one more unknown to solve for. That means we need to have a point on the curve where we can plug in its respective x and y coordinates to allow us to solve for this other unknown b, the y-intercept, right? And so that means that we're going to use x equal to pi plug that into f of x, because if we plug in an x coordinate into f of x, then we get its y coordinate, right? We need a point on the original curve. We want to know the actual coordinates of this point in space, right? And so how do we get the y coordinate if we have the x coordinate? We plug it into the function, right? F of x is the y coordinate, right? And so let's go ahead and do that. F of pi, right? Again, plugging in the x coordinate into the original function, get the actual coordinates of this point in space where the tangent line is going to graze the function f of x, right? And so f of pi means just plugging in pi in for x, and so we get pi squared times, again, that's cos of pi squared. Cos of pi, as we said, is -1, so -1 squared. And so without too much effort, we get the y coordinate when x is pi squared. So we have a point on f of x at pi for x and pi squared for y, right? And now we can plug in these respective x and y coordinates into our equation for the tangent line, right? We know m is 2 pi, and so y is going to take on the value of pi squared. M is 2 pi, and the x coordinate, right, that corresponds with the y coordinate of pi squared. The x coordinate is pi plus b. And now we just have one unknown with one equation, and so we can solve for b, right? We have pi squared is equal to 2 pi squared, right? And so that means that b is equal to, subtract 2 pi squares on both sides. What's pi squared minus 2 pi squares? Well, that's -1 pi squared. So that is our y-intercept for the tangent line, right? That's our b value. And that means that putting it all together, in the end, tangent line to the curve f of x at x is equal to pi is the line defined by the equation y is equal to m 2 pi x plus b minus pi squared. And that is the equation to our tangent line to the curve f of x at the specific point in space at pi and pi squared. So this is a useful application of derivatives. This is something we do a lot of in calculus. And so I hope this helps, and thanks for watching.